So we'll see together today what is the objective of this presentation through that element. What is a medical image? A medical image is a set of 2D slices in gray levels. And you can compare that to a satellite view of the Earth. And here you have a satellite view of a city. If you want to reach a road, a specific address, and if you don't have any map or GPS, it will be complex. So from the satellite view, there is algorithm on people who have extracted big arteries of the cities, giving name, and then thanks to the fact that we have several pictures of the same place but with different angle, it was possible to create 3D model that can be used for GPS. So the work we have performed is exactly the same, but from the satellite view of the patient, which is a CT scan or an MRI. We have developed algorithms that allow to extract the organs, the pathologies, and thanks to that, we can do a 3D modeling of the patient, and with the GPS of the surgeon, we can plan the surgery. It is the idea, and it is based on two past algorithms that we have first developed at IRCAD, the French Institute Against Digestive Cancer. It was initially what we have called the hierarchical approach. The idea is really simple to explain. You start, for instance, by extracting lungs. And when you have obtained the lungs, you look inside the lungs to segment, to delineate internal structure. By performing this kind of hierarchical approach, you reduce the difficulties, and you, for each element, it's simpler and simpler. Now, if you had artificial intelligence, the algorithm will be based on neural network, and here we have developed lots of new kind of neural network or new optimization of algorithm. It is based not only onto only one neural network, but onto several ones. And here you have an example onto these unit transformers. We use several unit transformers. Transformers is essentially because we want to have an analysis of the statistic position of the organ inside the patient. We are not working onto a cat in a picture. We are looking for organs. On organs, for instance, the liver is not outside of the body, but inside. And you know that the kidney are under the liver or in the back. So the position is known in advance, in average, and this average position can be provided thanks to the unit transformers. The other kind of algorithm we have used is a deep convnet neural network. Here the idea was to do a recursive analysis, and it's what I call the adolescent artificial intelligence. To explain what I mean, you know, in artificial intelligence, learn from a database, and this database is considered as the truth. But in reality, all databases are not perfect. There is error inside. And an adolescent, when you learn him something, will say you, I disagree with what you say me. And then you have to take a decision. Is the adolescent true or wrong? So it's exactly what we do. We ask to the artificial intelligence algorithm to analyze his learning database and to find potential error. And because it is an adolescent system, we control, because we are the adult, human control if he is right or wrong. And it is exactly what we have performed, and it totally optimized the learning database. It allows us to have obtained a nice algorithm that are certified. As you can see, we have a distribution thanks to Johnson & Johnson worldwide, and it works as an online service. The surgeon sends the image through a secure system. We do the analysis. Each analysis is double-checked by human, really important for the ethical approach, but also to be sure of the result, because you can never be sure that an algorithm will provide you a perfect result. And then we give back the result to the surgeon. We can do that for any part of the body because we have a certification for the whole body, and for any edges because we have a certification also for pediatric. And another important point, to visualize the result, we propose a free software that is a surgical planning software that you can download freely onto our website or onto Apple Store. What is the benefit to have such automatized modeling performed onto artificial intelligence? You can use it preoperatively to plan, you can use it intraoperatively to guide, like a GPS finally. And I would like to show you two examples that illustrate perfectly the amazing benefit. Here you have a 5-year-old patient with 2 tumors inside the kidney. The 2 tumors are in greens. And initially, the surgical planning without the modeling was resection of the total left kidney and half partial nephrectomy of the right kidney. You see here the result of 3D modeling, and what is really interesting is the possibility to do simulation of clip applying. That means the territories that can be cut, and the software will compute the volume. So here you see the right kidney. If you remember ACU that they plan to cut only half of the right kidney, so you see here the arteries and vein. With the software, you have only to click onto the right button onto an artery, and you immediately see the territory that is unvascularized with the volume. So here we put 2 clips, and we see that there is 39 cc of remaining kidney for right. For the left, you see an anatomical variation with 2 arteries and not only one. The upper one has to be clamped because it's the main one of the tumors. So we clamp this upper one. And you see with the security margin that you have to clamp a second artery here. And if you do that, you obtain, as you will see, 24 cc of remaining left kidney. It's a really small percentage of the left kidney, but when you add 24 and 39, you obtain 61, and the normal size of a kidney for the age, for the size and the weight of this child should be 60 cc. Thanks to that, you see the result. The surgery was totally changed. The child had a partial nephrectomy of right and left. He had his surgery in January 2018. In February, it was at school. He never had any dialysis, never had any transplantation, and he has a normal life like everybody. First example. Second example here, onto a lung. It has also a publication if you want to follow the result. What is interesting here, you see there is a double pulmonary sequestration, one on right, one on left. It was a diagnosis initially, so normally you have to resect these 2 sequestration. But the team has some difficulty to really understand where are the vasculations. They ask for a 3D model. So we do the 3D modeling again. So you see here the patient, we remove the skin. We will put under transparency the lung after removal of bone to see better. And when you put under transparency the left lung, as you will see, so in green it is a 2 sequestration. When you put under transparency the left lung, you will discover something really surprising. You see that the lower part is not inside the left lung. Indeed, the left lung is totally safe. And so the lower part you see here is the same sequestration that you have on the right, because when you put under transparency the right lung, you see that they are totally linked. Indeed, it's what the author call a horseshoe intralobar lung sequestration. So this left part is in reality a right part that has merged, that has switch into the left part of the patient. So the surgery is, of course, totally different. Thanks to the 3D model, again, you can plan your surgery really efficiently. You can remove here, for instance, the esophagus to have a better view onto the arteries and veins. You see here, by zooming the different arteries, we will remove the veins to have a better view onto the small arteries coming from the aorta. It is what we call the sequestration. And you will discover with really precise details that there is indeed 4 arteries coming from the aorta that you have to clamp before to do anything. It is really important. So you understand it has totally changed the initial planning. Indeed, in reality, there is an amazing number of benefits to use such modeling. You have here the list of these benefits, a better diagnosis, of course, a better surgical planning because you have the patient map. Of course, if you want to reach a road, it's better with the GPS than without. You have a reduction of the surgical length, which is really important because half an hour, it's $1,000. And in Europe, it's a little bit less, but you will save money only by this modeling. You have lots of optimization for kidney surgery. You see the ischemia typically. And we have a reduction of blood loss. Of course, you know in advance where are the arteries. And a reduction of the post-morbidity complication. For lungs, only to give you this example, for instance, you see that a consensus conference of this summer say that you mustn't do a segmentectomy with a segmentectomy on lung without modeling because it is highly recommended to use it for simple reason. You have a better location of tumors, but essentially you know all the variation. In France, we have obtained a coverage of this modeling for a large number of private insurance. As you can see, and now we work a lot in order to obtain the public coverage. It should be in 2025, in the later time, perhaps next year. So this is the beginning of what we try to do. You have heard about artificial intelligence. You know that Iron Man used Jarvis. So we have developed a software for the HoloLens. This software can be used intraoperatively really easily to visualize the same patient during the surgery. You see it's an hologram of the anatomy, and it is highly useful when you want to know where you are. Again, the idea of GPS. You have your map under your eyes when you navigate. And in the future, what will be, of course, the future is what you will see now. It is augmented reality. That means that you can see through the patient. So you see here, the surgeon sees through. He can do a tool placement, ideally, in order to take into account the position of organs. With artificial intelligence, we work a lot now onto the real-time deformation, but it illustrates what will be this future. So to conclude, you have, I think, understood 3D modeling is what we call the first step of digital surgery. It is performed thanks to augmented reality, to artificial intelligence, and in the future, it will be career guidance. Thank you for your attention.